Coulomb's law of electrostatics. Now, the last lesson we looked at Kirchhoff's law and also internal resistance and EMF. So they are more on the current part, the current voltage and resistance and the calculation, right? So we studied current, which is the movement of charges. Current involves the movement of the flow of charges. But today we will look at the study of static charges, okay? Electrostatics. What are the force produced from static charges? What are the field? How does the field interact with another field? Okay, and then the strength of all this field, what is the effect of it on other charges? So today our main focus is on static charges. Okay, so we call the Coulomb's law of electrostatics. Now, let's start with what does the law says. Okay, very simple. I have two charges, positive, negative. Now, if you think of a charge, what is really a charge? What is it? What is it? Is it something that we can see, we can hold, we can touch? Okay, what is really a charge? A charge is like a characteristics of an object, just like mass. How do you explain mass? You cannot explain mass, right? Mass is already there, right? It's something that exists fundamentally. So if you ask about what is mass, mass is actually, we say, the best way we can say is it is a property of the object. Every single object has mass. So if you want to explain what is charge, charge is just like mass. It is the property of a particle. Okay, every single particle, they have their own property, but all particle, they have, not all, sorry, charged particle, they have a property, is called the charge. All right. Now, suppose that we have two charges, positive and negative, and if you place it together, then this will be a force of attraction. Okay, so force pulling this one towards here, force pulling this one towards here. According to the Coulomb's law, we can actually calculate this force. Okay, it's given by F equals K Q1 Q2 / R squared. If you see this formula is actually the same as the gravitational attraction, the Newton's law of gravitation, where you have F equals to G M1 M2 over R squared. Okay, but this one applies on charges. Now the K, just like the G, is a constant. What is the value of the K? The value of the K is 9 times 10 power of 9. This one I can express as K equals to 1 over 4 pi epsilon naught. Okay, what is this epsilon naught? This epsilon is called permittivity. Permittivity of a medium. And the value of this epsilon is 8.85 times 10 minus 12. It's a constant. So if you put in here, you calculate the 1 over 4 pi, then you get the K as also a constant, 9 times 10 power of 9. Okay, if I know the charge Q1, Q2, and I know the distance of separation, I can calculate the force that is pulling these two particles towards each other. And the force is the same. If this one has a bigger charge, this one has a smaller charge, but both will experience the same force. Doesn't mean that the bigger one will experience the smaller or bigger force. No, it's the same. Okay. Now, what is really permittivity? You see, these two particles, they are separated at a distance. So what is the spacing between these two particles? This is the medium, right? It can be anything. It can be water, it can be air, it can be vacuum. So the point is that there's a medium between the two particles. Okay, so I want to think of permittivity like this. Just like any other characteristics, like temperature, pressure, all these are characteristics of a medium, right? A medium, you can think of it like, okay, let's say air. It has a certain temperature, a certain pressure. So these are the characteristics of the medium. You have temperature as the characteristics, pressure also. So permittivity is also one of the characteristics of the medium. But what is it? Permittivity is a measure of whether the medium allow or not allow the force to act. I repeat, you can think of permittivity like a characteristics of the medium, whether the medium allow or not allow the force to be acted. Okay, because the way you imagine is like this force, right? If this particle wants to pull this particle towards it, okay, let's say here, positive. It has a certain force. This is the field. Let's say 100. Okay, it got 100 field. It tries to pull this minus towards it. This force, it has to pass through the medium, right? It has to pass through the medium. But this medium, how many force can go through? Is it going to be 100 can go through or half of it? How many force can go through depends on the ability of the medium, whether it allow or not. Or we can say whether the medium got absorbed the force or not. Let's say 100 go like this, and then you got 60 absorbed by the medium. Then how many reach here? You have only 40 reach the other charged particle. So where is the 60? The 60 got absorbed. Which one, how many force that can go through? 40 can go through, 60 is absorbed. Okay, so that is the permittivity of the medium, whether medium allow the force to cross or not. So if you think about like that, more permittivity means what? More permittivity means less force. Okay, different medium has different permittivity. If you've got medium that has more permittivity, then the force is going to be less. Yeah. So they fixed that. They found that the permittivity of the medium for vacuum, okay, for vacuum or air, we can use the same for vacuum and air, is 8.85 times 10 power of minus 12. Okay, and you put in here, you get the constant 9 times 10 power of 10. Okay, now look at this equation. This is the equation, of course, you have to remember this lah. This one. What is the unit for the permittivity? Okay, put in here, we get F equals to Q1, Q2 over 4 pi epsilon R square. Okay, exchange place this one with this one. And we get epsilon equals to Q1 over Q2, 4 pi F R square. Okay, then we change to unit. This one equals to Coulomb times Coulomb over 4 pi Newton times meter square. So what do you get? C square, Newton minus 1 and M minus 2. This is the unit for permittivity. So 8.85 C square N minus 1 M minus 2. Or sometimes you see they use F M minus 1. The F is farad. Okay, farad per meter. Farads per meter. Okay, so for how much is, what is the unit of farad? Is actually C square N minus 1 and M minus 1 if you separate this one. Okay, so that is the on the unit. All right, example. Calculate the force between 2 point charges. Let's say we have 2 point charges. Positive, this one is positive. Okay, 100 microcoulomb. And also here, positive as well, 100 microcoulomb. And they're separated at a distance of 125 cm. Okay, I want to calculate the force. Okay, so F equals to K Q1 Q2 over R square, 9 times 10 power 9 times, same charges, right? So I just do, okay, you have to convert, times 10 minus 6 times another one, we just put it square over. Okay, and 125 times 10 minus 2. Okay, calculate this one, we get 57.6 Newton. Okay, what if one is negative charge? If this one is negative charge, if the other particle is negative charge, and when you calculate the force, okay, let's do when one is negative. Then you do F equals 9 times 10 power 9 times 100 times 10 minus 6. And then the charge for the other one, you have to put a negative. Okay, negative 100 times 10 minus 6. Okay. This one is a square, I forgot here. Square. Okay, divided by 125 times 10 minus 2 square. Okay, now when you calculate this, you get minus 57.6 Newton. What does the minus indicate? The minus here indicate that it is an attractive force. Here, the positive sign indicate that it is a force of repulsion. Right? So what we discuss here is how much is the force? Okay, how much is the force that is acting on the two particles? What is the effect of the force? Here, we know how to calculate how much, okay? But what is the effect? We know that the force acts on these two particles is 57.6 Newton, 57.6 Newton. The same force acts on both, but do they have the same effect? Does the force produce the same effect? No, because, okay, in some cases, no, because it depends on the mass, all right? So considering if this one is the same mass, then they will have the same effect. Both are having a certain acceleration. But if you have a bigger charge here, okay, plus Q, let's say this is 2Q and this is Q. Different charges, force is the same, but the effect of the force on the charges is not the same. Okay, the effect of the charges on the force. If this is 2m, this is m, twice the mass of it, then this one will have a greater or smaller acceleration. F equals to ma, a equals to force over m. If the mass is big, the acceleration is small. So same force acting, but the 2m is going to have a smaller acceleration, but the m will have a higher acceleration. So what is the point? What is the thing that I want to stress on you is that the same force is acting, but the effect of the force on the mass is different. It depends on the mass. Okay, so if you, let's say you do like a proton, okay, you take a proton, you take an electron here, you hang it like this, okay, like this. They wait, let me do like this. Proton, electron, they have a force of attraction, right? So they both accelerate towards one another. But the electron, if you compare the masses, electron is a few thousand times smaller than the proton. So the electron will accelerate greater, but the proton will move slower compared to the electron. Okay. Same as the gravitational, right? So Earth and Apple, same force pulling them, but the Apple accelerate downward. The Earth doesn't accelerate because of the huge mass. So everything that you learn in the gravitational, it can be applied in the electricity, electrostatics. Okay, you just convert the mass into charges. What you learn there applies here. Actually, this one should be taught right after the gravitational, but because of the sequence, so now only we look at the Coulomb force. The correct sequence should be gravitational. After you finish that, then straight we jump to Coulomb's law. Okay, now I go to the next slide. So here we have discussed two charges. We'll apply force. Huh? So now next one, we will look at where does the force come from? Okay, where does the force come from? Now, we have so far understood force can be categorized into two. One is contact, another one is non-contact. Contact force requires the object to be in contact. Non-contact force, for example, like field force, gravitational, magnetic, electric. Okay, so whenever there's force, that means the charge is placed in a region where there's a field. Okay, now mind the word here, I'm talking about electric field. So let's look at the field of a charge, right? So every single charge will create a field. So if I say that there's an electric field here, you know somewhere there must be a charge. The charge can be, okay, it could be here, it could be here, it could be at very, very far away. But whenever there's a field, there must be a charge. Okay, huh? So how do I know whether here, let's say in my room here, how do I know whether this got electric field or not? Very easy. I take a test charge. I take a positive charge. I will call it a test charge. I put it here. If this charge is not moving, then I would conclude that here, there's no electric field. But if I see the charge doing this, go here, it's moving. That means a force is produced, and I would conclude that we are here in an electric field, because only electric field can apply the force on a charged particle. Okay, so how do I know whether I'm in a field? I just take a test charge. If the test charge accelerates, then I know here is electric field. Whose electric field is this? Whose electric field is this? Okay, I don't know, but I know that there must be, the source must be somewhere. Maybe infinity, maybe nearby, I don't know. Okay, but whenever there's field, there must be a source. Okay, now I will write here a charged body, only a charged body generates electric field. Now you need to know how to define it. How do we define electric field? In the exam, you will be asked about definitions. If you look at the past year's question that I send every time, always the first question is the definition. Okay, the first question is the definition. So how do you define this one? It is a region. Okay, I have it here in my next slide. Wait. Okay, this one. A region of space where another charged particle will experience a force. The keyword charged particle, not charged particle will not experience a force. So if you place something that is not a charged particle here, you say that this is not, we are not in an electric field. No, you may be wrong, because this is not charged particle. It has to be a charged particle here. Okay, so a region of space where another charged particle will experience a force. All right. Now, how do I draw the electric field of a charge? Here, we have a positive charge, and you know electric field is represented in field lines. Okay, we draw lines. What are the field lines? Okay, look at here. Electric field lines, an imaginary line showing the direction that a positive test charge would take if it is placed inside electric field. So let's say you place a positive test charge here. If I place it here, then where will it move? You know, obvious. So it's going to repel, right? It's going to repel. So the movement forms the electric field lines. You have to follow the movement. If it's moved away, then your electric field line is pointing away like this. It has a direction. Okay, so you have to show it is a vector. Here, electric field This is the direction outward of the positive charge. Okay, now what about a negative charge? A negative charge here, then I put a positive test charge. Our test charge is a positive always. What will happen to the test charge? It will move towards it, right? So we use the motion. We use the motion of the test charge to make our electric field line. This is our electric field line. And it is pointing, where is it? Inward, here. So how do we define the electric field line? An imaginary line showing the direction that a positive test charge would take, okay, if it is placed inside electric field. That's how you define it. All right, now, when the charge moves like that, current is the flow of positive charge. And you know current always flow from high potential to low potential. So when positive charge flow in this direction, that means the closer you are to the positive charge, the higher will be the potential. This is high potential. Outside here is low potential. Okay, so if I say, example, I put two charge plate here. Here I connect to Earth, right? Anything that connected to Earth, the potential become how many? The potential becomes 0. Okay, here the plate is Earth, so it has 0 potential, and here I connect to positive 700 volt. All right, so there's a potential difference between here. If I want to draw the electric field, how do I draw the electric field? Imagine I place the positive charge here, it will repel, it will go towards here. Why would it go down here? Because positive charge, they always go from higher potential to lower potential. So it goes down here. Then I will draw my electric field lines like this here, pointing downward. Okay, if I say here, I apply negative potential. Here I connect to Earth, 0, and here I put negative 700 volt. Then how does my electric field look? Here, because this is negative potential, so if I put the test charge here, what will happen to the test charge? It will be attracted to the negative plate. So the motion shows the electric field. So we draw the electric field upward. Okay, again, where is high potential? Where is low potential? Here is high potential, even though it's 0, but it's higher than this. So here is low potential. This is high potential. This is low potential. Okay, now, why do we need to know electric field? And what is the relation with the Coulomb's law? You see, Coulomb's law allows you to calculate the force between 2 point charges. 2 point charges. What happens if I have more than 2 points? If I have more than 2 points, then I would use the electric field to help me to find out what is the result. So Coulomb's law is for 2 point charges, but electric field allows us to see when you have more than 2 charges, what will happen to the charge by studying the electric field of the charges. For example, let's say here I got a positive charge, and here I got a positive charge, here I got a positive charge. Also here I put a positive charge. Let's name this as charge A. Okay, now here I got so many charges, 4. But what is the electric field? This one. You know that the electric field is always, the line is always outward, going outward, right? So I can draw the one particular line that is joining this to here. So the charge A will experience a force from this charge that is going in this direction, F. Okay, same for this one here. This charge, how does the electric field line look? Outward. Okay, but I'm only going to draw this line that stretches to this point. and I see the effect on this charge. This is the force produced. Okay, same here. I do the same here. This is the lines like that. So I draw this one, stretch to here, then this one will produce a force here, F. This is positive charge, so it will be repelled in these three directions. The force, these three forces add up, you get the resultant. This is how we study. With the help of the electric field, we know what is the result on the charged particle. Okay? Right, now, electric field produce electric force. So if I want to know how strong is the field, just like our gravitational field, I want to know how strong is it. How do I measure how strong is it? What defines the strength of the field? Here's how we measure it. We take a charge, positive charge, test charge, we put it in this room. Okay, then I see the force push it here. I calculate the force and I calculate the charge of this test charge. Let's say I do 1 coulomb. Okay, I do 1 coulomb and then I observe if I place it in this electric field, it's going to move like this. Now I take the same charge, now I put it in another room. And then I observe the same charge, 1 coulomb, but now it goes faster like that. So what is my conclusion? I will conclude that the other room, the field will be stronger. The field on the other room is stronger because it applies more force on the same unit of charge. So we use that to define the strength, or we say the electric field intensity. So what is electric field intensity? Here, the same coulomb, how much force is pushing it? I put it in another room. The same coulomb, more force is pushing it. I put it in the third room. The same coulomb, larger force producing it. So I will say intensity is force per unit coulomb. Okay, force per unit coulomb, or F divided by Q. That becomes my equation for field intensity. Okay, this is like your gravitational field strength. W equals to mg. G equals what? W over m. How much weight per unit? Okay, just now got cut off a bit. Okay, I will repeat. Now, so E intensity is force per unit coulomb, same as the gravitational field strength. So how much force per unit mass and how much force per unit coulomb? Okay, what is the unit for this? Newton coulomb. So this one becomes Newton per coulomb. That is the first formula for electric field intensity. Okay, electric field intensity. Now, suppose that, again, two charges, Q1, Q2. Charge number 1 has electric field acting on charge number 2. Charge number 1, we bring it so far that we cannot see Q1. So we are only seeing the electric field of Q1. Now here, the Q2 is being placed inside the electric field. The intensity of the field I know is F over Q. So I will look at how much force acting on this Q2. How do I know the force acting on this? Again, the force acting on a positive charge is the same as the electric field direction. Okay, so if the electric field is along here, The force is along here. Okay, so E equals to F, and this Q is which one? Is it Q1 or is it Q2? Electric field equals to force acting per unit coulomb. This is Q2, right? Just like your Earth mass system. This is your mass. M1, Earth is M2. W equals mg. This mg equals W over m. What is the m? The m is the m1. Okay, it is the mass of the object being placed in the field. Same here, the charge of the object being placed in the field. So it is the Q2. Okay, Q1 we cannot see, this one very far. Okay, now, one second. Now, here I also know from Coulomb's law, force equals to KQ1 Q2 over R squared. Okay, now is it the same force? Yes, right. This force is the same force as the Coulomb force. It's the same force as this one. So I can equate them. From this equation, E equals to F over Q2. I can write F equals to EQ2 okay, EQ2, and then here I equate them. EQ2 equals KQ1 Q2 over R2. Cross, what do we get? E equals to KQ1 over R2. Again, you have the second formula. This is the first one. This is second one. Here. Electric field strength is equals to KQ1. This one, be careful, Q1. It is the source that is producing the field over the R2. So the R2 would be the distance between here. This is, we are considering point charge. Okay, a charge that is one singular point. The K, I can also write it as 1 over 4 pi epsilon, like that. So sometimes you will see they write it as E equals to Q1 over 4 pi epsilon R square. Okay, now this field, does it change? Does the electric field strength changes? From the formula, you see that it reduces when the distance increases, right? The further you go, it reduces. In fact, it reduces on the square. That means any increase that is going to have a greater reduction. This is only for long distances, okay? For long distances. We call it, when the E changes, we call it a non-uniform field. So is the electric field produced by point charge uniform or non-uniform? It is actually a non-uniform field, considering long distances, great distances. If we take very small distance, the distance from 2 points, this point here, let's say I take over here, and this point, this distance dr is very, very small, then we can barely see the changes in the electric field strength. So in this very small distance, the field would be uniform. But if I take longer distances, then the field will become non-uniform. This is one important thing, okay? You want to take note. And if you look at like a charge, circular shape, and if I draw the field, the further you are away, you can see the lines spread out, very obvious. But if you are very close to the center, then you can see all the lines are actually like parallel. Okay, so actually the field of a point charge is a non-uniform field. How do we make a uniform field? A uniform field is when we take very small distance in the field, just very small distance. Then we get a uniform field. What happens in a uniform field? The electric field strength is constant. Okay, the electric field strength is constant, just like your gravitational field strength. 9.81 is constant at small altitude. What happens when you go very far, huge altitude? Then it changes. Same for the electric field. Okay, now the graph part. The graph part, how do I plot this? E is inversely proportional, okay? The inverse square law, 1 over r squared. How do you plot that? Here. This one is E inversely proportional to r. If you have a square, then the gradient would be steeper like that. Okay, this is E 1 over r squared. Okay, what is this? E, this is r. The graph, you need to remember, because they will ask you to draw to sketch the graph. Okay, now electric field, we have looked at the definition and Coulomb's law also. What about electric field density? I will write it here. Okay, electric field intensity or strength is measured by how much force acting per unit charge. Okay, so in this slide, we have looked at the electric field of a what? Of a point source, of a point charge. Okay, all the things that we talked about just now is focused on point. What happens when I have different shapes, like a wire, a line, or a sphere? Okay, how does it changes the electric field? Because you see, any object, I can give it a charge. I can charge it. If I have a straight line like that, I charge the line. I give it charges. Then how is the distribution of the charges? The distribution is going to be along it, so in one line. What about a sphere? If I give it a charge, then the distribution will be all over the surface of the sphere. So in the next part, we will look at different shapes, different objects will give different types of electric field. Okay, now here. Now you want to remember again, before I raise this, you want to remember all these formulas. Apply for what? Apply for point charges, okay? Apply for point charges. Especially this one down here, okay? E equals to KQ1 R squared. This is apply for point charges. Okay, let's see. Now, let's say I have a, okay, this is a point charge plus, and this is a point charge plus. So this one is very straightforward. Straight away, you can see the field go like this, and then the force along it like that. So it will accelerate in this direction. What about if I have an object that is a straight line like that, like a wire? If I distribute the charge on it, then the charge will go along the line like that. Then if I put a positive charge here, where will the charge go? Okay, where will the charge go? Let's say here I give it 10 Coulomb. Here also 10 coulomb. The same charge, but the distribution is different. Okay, the distribution is different. This one is distributed such a way that it goes like a line. So how would it affect the electric field? Same, here I draw the line. At this very tiny point, we treat it as a point charge at this position. So the line goes like this, then it will experience a force in this direction. Same here, we take this one down here. The field extends to here, then the force will be like this. What about the middle? We take 3 points. At the middle, again, it goes like this, and then the force go like this. These three, you add up, you get the resultant to the right. So how does the electric field look for a straight line? Remember, how do you draw electric field? The electric field line is the same as the movement of the test charge, right? So where does my test charge move? That will be the line of the electric field. So in this case, the test charge will move like this. It will move to the right, because this one, I can resolve it, right? This one, it has a component vertical. It has a component horizontal. This one, it has a component vertical. It has a component horizontal. These two vertical will cancel off and leaving only the horizontal component. Okay, so for a line of charge, how does the field look? It actually looks like this. All this extending out horizontal like that. That means if you put a test charge nearby, it will go in this direction. Is this stronger or the point charge stronger? The force experience, you see, this one, all the force is acting on the charge. The second one, some forces are lost to the vertical component. This force, they are lost. The same charge from the source, 10 coulomb, 10 coulomb. But this one, some are acting at the vertical. So the force resultant must be less than the first one. Because you have more distribution of the charge, then the force acting, the resultant force will be less than a point charge. Okay? Sometimes you have a line that is very long, like a wire. Okay? Like the distribution of electricity in all regions of the country, right? The distribution, the transmission line, very long. Okay? There's a line of charges. So this is the electric field. Now, this is 2D, right? 3D, how does it look in 3D? 3D, this is like cylindrical, right? Like a cylinder. So all this field line, they extend like this, around it, all around it, like that. It looks like a bristle, okay? Like the brush that you use to clean the inside of a bottle. Okay, so you have the brush here, and then you have this, all this bristle extending outward in a straight line like that, all around it like that. That is the electric field of a straight wire, of a line. Okay, now take this one, the electric field of a line, and then we make it a sheet. First is a line, I make it now a sheet, like a plate. Okay, then you get two parallel plates, like a capacitor, like that. This one all positive, this one all negative. So if I put two parallel plates like that, this one is a sheet, you have the charges distribute over the sheet. Then the electric field goes like this. At the end, is actually curved a bit. At the end is a little bit curved like that. Okay, these two plates are taken very small distance, dr, so that it becomes uniform. When the distance is very large, the uniformity breaks. Okay, it has to be small. Okay, now, again, we will derive the electric field intensity for a parallel plate, this one. Okay, just now, the one that we did is for point charge, all right? That is for point charge. This one, we will look at the electric field intensity for a parallel plate. Okay, or I can say parallel sheet. Okay, now see. Suppose that electric field strength here. We take 2 points on the field, point A and point B, which is very small distance apart. Okay, so we have an electric field here with a source that is very far away. Now, this is the electric. You can think of it like a point source very far away. Okay, we take somewhere down here, 2 points very close. Now, here, small r, so field is uniform. When field is uniform, what does it mean in terms of the force? The force is constant. Okay, E equals to F over Q. So F equals to EQ. When this is constant, then the force is a constant. So between point AB, the constant force is acting on the charge. Okay, that is the first thing. Now, recall how do we calculate the potential difference? Potential difference between 2 points, A and B, is defined as the work done to drive a charge from B to A. Like a circuit, okay? Like a circuit. If I put a circuit like this is positive, this is negative, okay? Potential difference between AB. Okay, let me put this like that. Between AB, potential difference between AB is defined as work done to drive 1 coulomb of charge from B to A. It's opposite direction. Okay, that is the definition of the potential difference. Potential difference between AB, which one is larger? AB. A is larger because the current flow like that, right? Flow like that. So this one will have a higher potential. This one has a lower potential. You take the potential difference between them, so it's VA minus VB. That is the difference. Okay, the potential difference is equal to the work to drive 1 unit of charge from B to A. So we take that and we put it here. I can write the potential difference between this AB. You can think of it like this is a positive. Here is a negative, just like our circuit going from positive to negative. Okay, so potential difference between AB, VA minus VB, equals to work done to drive the charge from B to A divided by per unit charge, right? Because work done to drive 1 unit charge, so we divide by Q. Okay, now here VA minus VB, I'll just write it as dV, change in the V, equals to work done equals to force times distance. The force of electric field is acting to the right. This is the field force. Okay, this is our test charge. Force is the same direction as the electric field. So that means if you are moving the charge from B to A and your force is to the right, your work done is, it will be a negative work. Because your force and distance direction is not the same. You are moving here, dr, to the left, but the electric force is pushing to the right. It's the opposite, so you will get a negative work. So I would put here minus F times dr divided by Q. Okay, like that. Okay, next one. dV equals to, now, you already know F equals to EQ. Put that in. Inside here, we get minus QE dr over Q. Cross, cross, we get dV equals to minus E dr. And I rearrange this, E equals to dV over dr. The negative is over here. Okay, let me write that clearly. E equals to minus dV over dr. This equation, please remember this. This is a very important equation. What does it say? Let's look at the application of this first. Where do this apply? This applies for very small distance, right? Where the field is uniform, dr. Okay, apply the formula apply for very small distance where the field is uniform, so the field strength is constant, just like the parallel plate. So this formula, you can use it for every single parallel plate. Okay, how do we use it? Usually they will give you, okay, the potential difference between the parallel plate, 240 volt. Okay, and they are separated by, okay, 15 millimeter. Calculate the electric field intensity between the plate. Then we use this formula. Okay, E equals to dV, potential difference, 240 divided by dr, 15 times 10 minus 3. Divide 15 times 10 minus 3. We get 16,000. E equals to 16,000. What is the unit? dV over dr. dV is V, dr is meter. So you get 16,000 volt per meter. That is your E. This is the unit for electric field strength. You have another unit, that is the Newton per Coulomb, right? This is from the force divided by charge. This is one unit, Newton per Coulomb. This is another unit, volt per meter. Okay, so the formula for us to calculate, if you're given the potential difference and the distance of separation, then you can get the electric field strength. Same as if you're given the electric field strength and the potential difference, they ask you to calculate the distance of separation. We can use this formula here. Why there's a negative in the formula? Why there's a negative in the formula? Okay, you see, when the dr is a positive, that means we are going to the right. When we go to the right along the line, when the dr is a positive and when the electric field is a positive, we go along the line to the right. The dV is a negative. That means the potential decreases as we go along the line. Okay, I repeat, why you have a negative here? Because along the line of the electric field, when you go to the right, this is a plus, the dr is also a plus, then you will get a negative dV. That means that the change in the potential is decreasing. The potential is decreasing along the direction to the right. Okay, which makes sense because as the positive charge travel, it travel from high potential to low potential. So the potential decreases. Okay, why you want to know this? Because sometimes you will be asked, what is the significance of the negative sign? What is the significance of the negative? in the equation. How do you answer this one? Okay, then you write the negative sign show that potential difference decrease. Okay, it should be potential, not potential difference. The potential okay, actually it's the same. Potential difference decreases in the direction of E. Okay, so that's how you answer. In calculation, we don't usually write it this way. We just write E equals to V over R, or you see E equals to V over D. Right? But this is the general, right? But this is the general way of writing it. Okay, we can just write E equals to V over D. Okay, I will show you one example how to use this. Okay, very simple. You see here, two plates, plate A, plate B. B, we give it a potential of 600 volt. And let's say the electric field strength is 20 volt per meter. Okay, and the distance of separation is 10 meter. Find the potential of A, VA. Okay, then we do here. E equals to V over D equals to, we want to find the potential difference first. This one is potential difference, remember. So V equals to E times D, 20 times 10. That is 200 volt. What is the 200 volt? This is the potential difference. So the difference is 200. Do we add to the 600 or do we minus the 600? Okay, what do we do? Add or minus? We add to the 600. So this one become 800 V here. Sorry, I should have written the field here. It's going from left to right. Okay, why do we add to the 600? Is because the field is going from left to right. Potential decreases along the field. So this must be higher potential. So VA is 800 volt. Okay, now the graph. Let me clear a little bit this one. The graph is like that. E against R. So the distance of separation, whether be here, 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 the field remain uniform. So it's a horizontal line. Okay, so this is V over D. Because the field is uniform. Uniform field give you constant force. If non-uniform field, the force acting changes. Okay, the force acting changes. If the field is non-uniform, then point A, point B, here may be greater force, here may be smaller force. So if it's the same, then the force is the same. Okay, yeah. Our formula for the force, F equals to QE. Okay, now we will look at the next part, which is the last part, on the electric field of a sphere. Okay, now, just now we looked at the point. This one, we looked at the plate, electric field strength of a plate. And the last one, we will look at the electric field strength of a shell or a sphere. Now, I want to make something very clear. Okay, let me erase this first, just to not confuse with the sphere. Wait. Three types. This is a shell, is a conductor. This is a full sphere, also a conductor. And this is a full sphere insulator. Okay, this one is not many, just short one. Okay, I short one. After with this one, then I give you a break. Okay, three types, just not to confuse with one another. The first one is a shell. That means it's only the outer surface. Inside is hollow. Okay, only the outer surface. Inside is hollow. So that means it is a conductor, right? That means if I give it a charge, the charge will go to it only can stay on the surface. Inside is hollow. Okay, that is a shell. We can sometimes say a charged shell. Okay, a charged shell, or in your book, sometimes it says a hollow charged shell. It's the same thing, right? Now, the second one is a full sphere. Imagine that this is a metal, a conductor, okay, a metal, and the sphere is full. That means if I give it a charge, the charge can go inside, right? The charge can go inside, but because it is a conductor, the charge can flow, right? They can flow. If you give it all the positive charge inside here, what happened to all this positive charge? All this positive charge, they will repel. They repel from the center, they got repelled outward. So all these charges now, again, just like the first one, they stay at the surface. Okay, they stay at the surface. So all these charges, they repel one another, they move outward. And as a result, you get what? You get the charge on the surface as well, which is the same result as the first one. Okay, let me draw it here. This is initial. Okay, all this repel and they go outward. So that means leaving again no charge at the middle. This is a full sphere conductor metal. Now, insulator is a little bit different. Why? Because insulator, it does not allow the charge to move freely inside the metal. So that means if you have a positive charge here, then this positive charge is going to be stuck. Okay, it's going to be stuck in the middle. It cannot move. So what happens is that if you give it a charge, then the charge just stay inside. Okay, the charge just stay inside, like a cloud. One cloud collide with another cloud. This cloud is carrying positive charge. This cloud is carrying another bunch of positive charge. Okay, they combine, they combine together, and there's a friction, but the charge cannot move that much. Okay, because the cloud is not a good conductor. So what happened to the charge? The charge remained in the middle, in the center. They got mixed up here. Okay, that is the difference between these three: full sphere, shell, and the insulator one. In this section, we will not look at this one. Okay, we will not look at this one. And these two, they actually the same thing. Same because they produce the same result. So whenever I say hollow charge or full sphere, they are actually the same result. What is the result here? The electric field of, you need to know this one, okay, is that the electric field of a sphere, how does it look? Not how does it look, is how does it behave inside and outside? Inside the field, inside the sphere, the electric field is 0. Because the field inside cancel off one another. So you get a 0 field. Okay, this one will be asked. You need to know this. Why 0? Because the field got cancel out each other. This is actually based on the Gaussian law. But since that is not the main topic today, so we will not discuss that. Okay, but the field inside the hollow sphere or the full sphere, the net field is 0 inside. That is inside. Huh? Then outside the field, let's take this point P. Outside the sphere, at a certain distance away, there is a field. And at outside, it will treat the charge as if it was a point charge. Let me write it down here. Net field strength inside is 0. Okay, so inside is 0. And outside, field behaves as if all the charge creating is a point. Okay, so that is the 2 point here. That means outside, we are treating the charged sphere as a single point. So if we are treating it as a single point, that means our formula electric field strength of the point applies. Where do we get this formula? This is from the first one, right? The electric field strength of a point source. Okay, we have looked at the point, the line, and this is the sphere. Okay, so since it behaves at a point, so I can use this one apply. So if I sketch the graph of the electric field strength, E against R, this big R is the radius of the sphere. Okay, testing sound. Okay, you should be able to hear me now. Okay, now if I sketch the graph of E against R, this big R is the radius of the sphere. Then how does the graph look? Just now I mentioned what happened inside the sphere. The electric field is a 0. So here you will get a line on the x-axis. Okay, and then once you reach the surface, the R, and then once you go outside the surface, straight away your field will be like that. Here, and then right, drops like that. You can see this section of the graph on the right side of the R is similar to the one that we drew earlier. Okay, the one that is like this, right? This is E, the inverse square law, 1 over R here. That is outside the surface over here. Because outside the surface, it treated as a point source. So the graph is going to look like the same like this one. Okay, that is outside. What happened inside? Inside, the field cancel out, leaving 0 field, 0 field. So the graph looks like this. Okay, so that's how you. What is the value here? This value here is E, oops. The maximum value here is KQ over, if you put the radius inside, you get the maximum value of the field strength. Okay, guys, I give you a 5-minute break. After 5 minutes, we come back and I want to show you just one example on the typical questions of the exam, and then I will give you exercises to pass your questions. Okay, we'll come back at 8:20. Okay, we are back and we look at the one example. Okay, here, example one. Diagram shows a positive charge particle moving across the vertical plates. Right, so this one has a negative potential, this one has a positive potential. And electric field will be pointing down to up like that. Okay, so this is a vertical plate. Vertical plate. Now, calculate the electric field strength between the plates. Okay, so then we can use the potential difference and the distance of separation, right? E equals to V over D, 240 divided by 20 times 10 minus 3. Again, this one is the formula that for uniform field, right? So 20 times this one, 1.2 times 10 power of 4. Vm minus 1. Okay, B, draw the electric field and find the force acting on the charge. So we have drawn the electric field, and how about the force acting on the charge? We first label the direction. So this is a repulsion. The force always be labeled same direction as the electric field if it was a positive, right? If it was a negative, then where's the force? The force would be the opposite. Okay, so to find the force, we already have the electric field strength. So we would use F equals to QE. Okay, QE equals to this one. A charged particle, a proton. So the charge, we would use the charge of a proton, 1.6 times 10 minus 19 times 1.2 times 10 to the power 4. Newton. Okay, sometimes they give you like beta particle, alpha particle, then you need to know the charge. Let's say if they say this one is the alpha particle, then you know alpha particle is a +2. It's a +2, so you need to multiply by 2, depending on what they give you here. Okay, C, calculate the acceleration of the charged particle. Okay, so we're going to take F equals to ma, F 1.92 times 10 minus 15 equals to the mass given here, 1.67 times 10 minus 27 A. Okay, so A equals to this one, we get 1.15 and times 10 power of 12. Okay. Okay, next one, D, calculate the work done by the electric field. Work done by electric field, so we use the potential. Okay, the potential, we know that potential equals to the work done divided by Q, right? This one, in general, I can write it as the potential difference would be equals to the work done divided by the charge. Okay, so potential difference between these 2 points is the work done to drive 1 unit across it. So since we already know that 240 equals to W over 1.67, oops, 1.6 times 10 minus 19. And we calculate the work done. Work done is equals to 3.84 times 10 power of minus 17 joule. Work done by the electric field. Is it a positive work or is it a negative work? You see the force by the electric field. This one, this force is by the electric field. And the motion is also going up, direction of motion. So same as the force of the electric field. So the electric field is doing positive work. So your answer is a positive. Okay, so field doing positive work. All right, E. Calculate the gain in the gravitational potential energy. Now, you want to be careful with this one because the work done 3.84 times 10 power of negative 7 does not equal to the gain in gravitational potential energy alone. You also have kinetic energy, right? So for this question, we will do PE equals to, we just do the usual way, mgh, right? The change in the height equals to the change in the PE, right? So equals to 1.67 times 10 minus 27, 9.81 times the height is 20. Okay, so equals this one. If we calculate this, we get 3.28 times 10 minus 28. This is a rounded value to three significant figures. So when you calculate, you take all the decimal at the back. So that is the change in the PE. From here, rise up to here, to the negative plate. Now, what about F? Calculate the gain in the kinetic energy. So we know that the work done by the electric field to bring it up here would be the same as what? Would be the same as the gain in the PE plus the gain in the KE. Okay, so W equals to the change in PE plus the change in the KE. So using this one, we can calculate the KE. So KE, change in the KE equals to W minus change in PE. Minus 3 point, oops, equals to 3.512 times 10 minus 27 joule. Okay, that is the answer. What energy to what energy conversion? At first, the charge being in the field is electric potential. Okay, electric potential convert to kinetic energy plus potential energy. Okay, going from electric potential to kinetic and potential. The process is the work done. Okay, the process is the work done. So work done, how much is the work done equals to how much is the gain. This one is for vertical plate. If you have a horizontal plate, if I arrange the plate like this, plus minus horizontal, and then the charge go from here to here, is there any gain in the PE? No, no gain in PE. So in this case, your work done would be the change in the KE only because it's going horizontal. Okay, sometimes they give you like this, sometimes they give you like this one. All right, G. Calculate the gain in speed. Okay, you have the change in kinetic energy, 1/2 m change in the speed square. Wait, I think there's a mistake. This one is 1.03. Okay, now last one. Another positively charged particle of the same mass travel across the plate horizontally. Draw the motion of the particle in the field. Okay, for the particle travel horizontally, let me erase this one. This one, the same plate, but the particle move from here, same charge, same mass, and it travel across from left to right. Calculate the time it takes to travel across the plate. Now, the trajectory of the particle here would be, as soon as it enters, let's say it's here, the force will be pulling upward. Over time, the force will be pulling upward like that. Okay, so it will slowly deviate to the upside like this. This is the motion of the particle like that. Why there's a curve? Because the force here will create an acceleration. The acceleration is only upward. There is no acceleration in the horizontal component. Okay, so there's only acceleration in the vertical component. It's very important to know this so that in the horizontal component, AX is 0. So if the horizontal component acceleration is 0, then that means the whatever speed it is moving, entering the field, it will remain traveling at that speed. What is the speed? 5 times 10 power of 7. It will remain moving at 5 times 10 power of 7. So if I want to calculate the time it takes to travel across the plate here, speed equals distance over time, because speed is constant in the horizontal direction. Okay, so here, speed time equals to distance over speed equals to 15 cm divided by 5 times 10 power 7. That is going to be equal to 3 times 10 minus 9 second. So it's 3 nanosecond. That is the time to cross from this end across the plate from this end. That is the horizontal. The vertical is going to have acceleration. So there is going to have a change in the speed in the vertical direction. So this motion, sometimes it can be related to, what motion is this? Projectile motion. Okay, projectile motion, where you learn about the vertical component and the horizontal component. Sometimes they ask you, what is the vertical distance, deflection in the vertical? So then you need to use the vertical component to solve it, just like how you would solve the projectile motion.